I'm going to work the mean value theorem problem from page 217, number 6. This is in Foerster's text. Asks me to find the point x equals c guaranteed by the mean value theorem. Gives me the function 5 minus radical x. Gives me the interval 1 comma 9. So between x values of 1 and 9. So you can see I've got my interval graph down here. And here is my value of x equals 1. Here is my value of x equals 9. Remember what the mean value theorem guarantees. It guarantees that the slope of the secant over an interval, if a graph is continuous and differentiable on that interval, is going to, the slope of that secant is going to be equal to the slope of some tangent value of that curve somewhere within that interval. Okay, so the first thing I'm going to do here is draw in my secant segment, and I need to find its slope. Okay, slope of course is change in y over change in x. In this case the change in y is going to be 2 minus 4. The change in x is going to be 9 minus 1. That ends up being negative 2 over 8, which is negative 1/4. Alright, according to the mean value theorem, there should be some value at which the tangent slope should be equal. So in other words, if the average rate of change over the course of that interval is equal to negative 1/4, somewhere there should be an instantaneous rate of change also equal to negative 1/4 along that interval. So to find that instantaneous rate of change, the slope of that tangent, I can find the derivative of my function. My original function is y equals 5 minus, I'm going to write that as x to the 1/2 power. So y prime is equal to, derivative of 5 is 0. That's going to be negative 1/2 x to the negative 1/2 when I drop my power by 1. And that's my y prime value there. Let me make sure I use the correct notation. And I want y prime to equal negative 1/4. So I have negative 1/4 equals negative 1/2 x to the negative 1/2. I can solve that equation. I'm going to multiply both sides by negative 2. Okay, negative 2 times negative 1/4 is 1/2. That's equal to x to the negative 1/2. Okay, that's a reciprocal, a negative exponent. So that means that 2 is equal to x to the 1/2. I can now square both sides, and x is going to equal 4. Remember that that x value where the tangent slope is equal to the secant slope is the value that we normally refer to as c. So my value of c in this case is equal to 4. And what that says, back in my original graph, says when x is equal to 4, my secant line is going to have the same slope as my tangent line. And you can see kind of a general depiction of that here in this graph. So that's the concept of the mean value theorem. It can be viewed several different ways, but that's the key. Find the slope of the secant line. Once you find the slope of the secant line, you should be able to find the slope of a tangent line that's equal to the slope of that secant. Again, assuming that the graph is continuous and differentiable on that interval. Here are two other brief examples of the mean value theorem. First of all, this question asks me to find the value of c guaranteed by the mean value theorem of y equals x to the 2/3 power on the interval from x equals negative 1 to x equals 3. And take a look at what the graph looks like in this case. You're basically taking cube roots squared, if you want to think about what a 2/3 power does. And the graph looks like this. And we run into a problem because you can see as this graph approaches a cusp here at the origin, the limit of the slopes is approaching a steeper and steeper and steeper positive value. As the limit of the slopes approaches a steeper and steeper negative value on the other side, the two limits are not going to approach the same value. As a result, the function is not differentiable. There is no solution guaranteed by the mean value theorem for this question. Okay? Second example. If I want to find the value of c guaranteed by the mean value theorem for y equals 1 over x over the interval from x equals -2 to +2. Once again, you'll notice the graph, in this case, is not differentiable at x equals 0 because it's not continuous. And so in this case, this graph also does not meet the basic hypothesis required for the mean value theorem. As a result, no value of c is guaranteed. With that said, be careful. Just because a graph has a place of discontinuity, or just because it has a cusp, doesn't necessarily mean that it's not going to have a solution. You do need to take a look at the interval that you're looking for that solution on. It's possible that it could be continuous and differentiable on that interval. But in this case, both of these graphs are not going to meet the requirements of the mean value theorem, and as a result, we do not have a guaranteed value of c.